So today we're going to do a flipped lesson, which means you're going to watch the video and follow along on your worksheet. So right now you have a do now in front of you, 1 and 2. Take a minute to solve both of those equations to find all of the solutions. Hit pause while you do it, and then when you're ready to check your answer, hit play. So when we factor the first equation, both of those binomials can be factored further. They are both the difference of perfect squares. And then after it's completely factored, I can tee everything off and get all 4 solutions. So my answers are plus and minus 3, as well as plus and minus 4. For the next one as well, both of those can be factored further. The first is a trinomial, the second is a binomial. And now if you notice, I have 2 factors that are both x plus 1. So I can write it like this as well. And now we tee off. And we have 3 answers. But what we're going to see during this lesson is that x plus 1, because it's squared, it's going to have a special quality that relates to the graph. And we'll come back to that in a little while. So our goal for today is a couple of things. We're going to start to identify key features about polynomials, including zeros, multiplicities, degree, end behavior, and local extrema. We're not going to sketch during this lesson. We'll do that in a future lesson. So before we get into any of the actual identifying from graphs, we're going to have to take a look at some vocabulary. So if you need to, pause the video, copy down the definitions into your notes, and then hit play when you're ready to go. Polynomial. It's an expression with more than one term that contains non-negative integer exponents. A zero is where the graph touches the x-axis. It's also known as an x-intercept, a solution, or a root. Multiplicity is the number of times a given polynomial equation has a root at a given point. Degree, for a polynomial with one variable, the degree is the largest exponent. Tangent is something that touches at a single point without crossing over. So like I said, if you need, hit pause to finish copying down the definitions into your notes, and then hit play when you're ready to pick back up with the video. So we're going to fill out this chart. Each row has a specific graph, and we're going to talk about what that graph means in terms of its multiplicity and the way it behaves, and the zero, a possible equation, and the degree of the given function. So let's take a look at our first graph. If you notice, this graph looks like a line, and it passes straight through the x-axis. And that point that it passes straight through, for now, we're just going to label as x equals -3. So since this passes straight through the x-axis, it has a multiplicity of 1. So anytime we see something going straight through, we know that it has a multiplicity of 1. As we said in the definitions, a 0 is the same thing as an x-intercept. So our 0 here is x equals -3. Our possible equation is going to be y equals x plus 3. And I'm just going to show it to you with an exponent of 1 for right now so you can start to see the pattern. But we know that that exponent of 1 is not necessary. And this would be a degree 1 function. Our next graph touches the x-axis at x equals 0, so let's label that. And it kind of touches and then bounces and goes right back up. So this is a multiplicity of 2. It's tangent to the x-axis. It touches once but doesn't cross through, and it has a bounce. So whenever we see something like this, which we're going to call a bounce, we know that it has a multiplicity of 2. So our 0 is x equals 0. Our possible equation would be y equals x minus 0 squared, but we know that we really don't need that minus 0, so you could write it as x squared, but I want you to start seeing this pattern. So that's why I have it in parentheses with the squared on the outside. And this would be a degree 2 function, second degree function. If we take a look at our third graph, this graph crosses over the x-axis at, let's say, x equals 1. So let's label that. And this is what we know as a multiplicity 3. It flattens out before it crosses the x-axis. So unlike the first picture, it doesn't go straight through. It kind of squiggles through. So our 0 here would be x equals 1 because a 0 is the same thing as an x-intercept. And our equation would be y equals x minus 1 to the third power. And it's a third degree function. So if you notice so far, what's happening is our multiplicity is matching the degree, and it's also matching the exponent on the outside of the parentheses. Our last graph, if you take a look at that one, this we're going to say touches at x equals -4. And this one looks a little bit similar to the multiplicity of 2, except this time this is a multiplicity of 4, because although it's tangent to the x-axis, it's not exactly the same as multiplicity of 2. It flattens out a little bit as it touches the axis. Whereas multiplicity of 2 was a straight bounce, this one is a little bit flatter. So our 0, or our x-intercept, or which is also known as our root, is x equals -4. And our equation here would be y equals x plus 4 to the fourth, because we now know that our multiplicity matches the exponent, which also matches our degree. Okay, so if we take a look at this example, what's happening here is you're going to see that there's going to be multiple different multiplicities in a given graph. So they want us to classify each 0 of the function below with its multiplicity. And remember, a 0 is the same thing as a root or a solution or an x-intercept. So let's take a look at our first x-intercept. The first place this graph touches the x-axis is at x equals -3. And if you notice, it's a bounce. So at x equals -3, since it's a bounce, that means it's a multiplicity of 2. And now if we look at the next place it crosses the x-axis, or touches the x-axis, our next root, or 0, is x equals 2. And this one crosses through the x-axis, but it's a little bit flat. So it squiggles through, so that's going to be our multiplicity of 3, just like it matches the picture on the front in that chart that we filled out. And then our last 0 is x equals 5. And at x equals 5, it crosses the x-axis and it goes straight through. It doesn't linger or flatten out or anything like that. So since it's straight through, it's a multiplicity of 1. So now part B, we want to take all of those and work backwards to somehow get a possible equation. So we're going to work with each piece individually. I always start with a y equals because for an equation, we always need an equals. So if it's x equals -3, it's going to be the opposite. So it's x plus 3. Our multiplicity of 2 is going to match our exponent. Then I have x equals 2. So this piece is going to be x minus 2. This has a multiplicity of 3, so that's going to match our exponent, x minus 2 to the 3rd power. And lastly, we have x minus 5. You could put to the 1st power, but remember, you don't need to. So now part C says, what degree could this polynomial function have? Well, we know that the degree matches our multiplicity. But now, since we have multiple different pieces, we're going to add all of our multiplicities together. So 2 plus 3 plus 1 gives us a 6th degree function. So just so we can recap that, how are the multiplicities of the zeros related to the degree of the polynomial function? We add all of our multiplicities together to get the degree. Okay, so we just talked about graphically how we can identify multiplicities. Well, we can also identify multiplicities algebraically or from an equation. So the directions say in examples 1 and 2, find the zeros of the given polynomials functions as well as their multiplicities. So to determine the zeros of a polynomial algebraically, we already know this. We factor, tee off, and solve. And to determine the multiplicity of a zero, we're going to look at the exponents. So make sure you get this down in your notes. If you need to pause, that's fine. We're going to do example 1 together. Then I'm going to let you try example 2, and you'll be able to pick back up with the video to see if your answer is correct. So number 1 is already in factored form, which is great. So I'm just going to tee off. I get x equals 4 and x equals 2. And my multiplicities match the exponents. So this is a multiplicity of 3 for x equals 4 and a multiplicity of 8 for x equals 2. So pause the video, try number 2 on your own, and then hit play to check your answer. So for this one, I'm setting it equal to 0. We have to do a little bit of solving. So I'm going to get x equals 3/2, which is my 0. And the multiplicity is going to match the exponent. So it's a multiplicity of 5. All right, so now we're going to talk about the shape of a polynomial. Because the shape of a polynomial function is going to depend on its degree. So if we take a look at the first picture, our first picture is a quadratic function, which means it's a degree of 2. Quadratic is a degree of 2, so it has like an x squared. And a quadratic function, since it has a degree of 2, can have up to 2 roots. So if I take this and just watch, because you don't have this line in front of you. So if I take this line, and this is like my x-axis, the quadratic function could be tangent to the x-axis and bounce, which would give it a single root, but it would have a multiplicity of 2. Or if I move it up, it would cross the x-axis 2 times. So a quadratic function can have up to 2 roots. If I took it and I moved this, and I moved the line, let me just lock this other piece in place so it doesn't move on me. If I take this line and I move it down here, it touches 0 times. And we're going to see that that will eventually mean there are imaginary solutions or there are no real roots. So now if we take a look at this graph, maximum and minimum, there is one max or min. A maximum or a minimum is like a turning point. So now if we move on to our second graph, this is a picture of a cubic function. Cubic function is degree 3, which means it can have up to 3 solutions or up to 3 x-intercepts or zeros. So if I take my line and I move it over here, it would have 1 solution. If I keep moving up here, it would have a single root and a double root or a multiplicity of 2 where it bounced. So it would only have 2 solutions. And then if I keep moving it up even further, it would have 3 solutions. And if we take a look at our maximum and minimums, there's 1 max and 1 min for a total of 2. Now if we take a look at our quartic function, that's a degree 4. So that means we can have up to 4 solutions. So let's take a look. I can have 1 solution. I can have 2 solutions. And remember, my solutions are the same thing as my x-intercepts. So in this case, it's where it's crossing the line. So if I go back here, it touched it once. So that would be 1 x-intercept. If I move it up here, it would touch it twice. If I keep going, this would be 3 times or 4 times. So these are all different possibilities for a quartic polynomial. It can have up to 4 real roots or real x-intercepts. And if we take a look at our max and mins or our turning points, this time we have 3 of them. Lastly, on the right, we have a quintic. That is degree 5, which means it can have up to 5 zeros or up to 5 x-intercepts. So here would be 1, 2, this would be 4, this would also be 4. So it's just going to depend on what the picture looks like. But we know that based on our degree, there can be up to that many x-intercepts. And if we take a look at this, 1, 2, 3, 4 turning points or 4 maximum and minimums. So the word local extrema is going to come up. It came up in our target earlier. Local extrema is just a maximum or a minimum, a turning point in its neighborhood. It's called a local extrema because it's in that general area. It's not going to be the maximum of the entire polynomial function, but in its general location, it's considered a maximum or a minimum. If we go back up here and we take a look, for example, at this quartic function, there are 2 local minimums. Right here would be a local minimum because in its area, it's the lowest point. And then over here would also be a local minimum because in its area or in its neighborhood, it's the lowest point. So the one on the left, even though it's not the lowest point in the entire function, we still call it a local minimum. And if we take a look at the relationship between the degree and the max and the mins, you should notice that your maximum and minimums is always going to be 1 less than your degree. So if I have a cubic function is degree 3, I can have up to 2 max and mins or up to 2 local extrema. Just like I can have up to 3 zeros or up to 3 x-intercepts. So that's are shapes of polynomials, how they relate to the degree, which is also related to our zeros or x-intercepts, as well as the local extrema. So now we're going to move on to end behavior of a polynomial. So end behavior is a way to describe what happens to the function as x approaches positive and negative infinity without having to draw the graph. So let's just fill in end behavior because this is our definition. And we're going to take a look at a graph, and I'm going to show you some notation that you're going to start seeing and you're going to need to become familiar with. So first things first, I want to put arrows on this graph so that we're going to predict what's happening as it keeps going. So if I look at the right side first, the right side, my arrow is pointing up. And remember, we're going to predict what's happening as x approaches infinity. So as x approaches infinity, which means as I'm going further and further right, what's happening to my graph? My graph is going up. So the closer I get to the right to positive infinity, the higher my graph gets. So f of x is going to be approaching positive infinity as well. And remember that y is the same thing as f of x. That's just function notation. So now if we look on the left side, we have the graph going down. So over here, as x is approaching negative infinity, which means as I go further and further left, what's happening to my graph? My graph is going down. So that means that f of x is going to negative infinity as well, because it's going down. So we can predict end behavior based on the equation of a polynomial. And there are 4 types. We can have an even degree with a positive leading coefficient. And it's going to look like this, where they both point facing up. So as I go further and further right, if I'm pointing up, my graph is going to positive infinity. As I go further and further left, or as x approaches negative infinity, my graph is still pointing up. So it's approaching positive infinity as well. So that's even degree, positive leading coefficient. Next is even degree, negative leading coefficient. So it's going to be facing down. Whenever we have an even degree, they both face in the same direction, and because it's negative, they're pointing down. So if I'm going to the right, as x approaches infinity, where is the graph going? Our graph is going down, so that means that it is approaching negative infinity. As x approaches negative infinity, which means I'm going to the left, the further and further left I go, where is my graph going? My arrow is still pointing down, so I am approaching negative infinity. So what's important is even degrees always match. They're either both up or both down. Odd degree. Odd is always opposite. So unlike even, where they're both facing in the same direction, odd, they're going opposite directions. One arrow points up, one arrow points down. So as I go to the right, or as x approaches infinity, my arrow is going up, which means that my graph is approaching infinity. As I'm going to the left, as x approaches negative infinity, the further and further left I go, my graph is pointing down. That arrow is pointed down towards negative infinity. And lastly, if I have an odd degree negative leading coefficient, our graph's going to look like this. It's opposite. So as I am going to the right, or as x approaches infinity, my graph is pointing down. The graph is pointing towards negative infinity. As x approaches negative infinity, which means I'm going to the left, so the further and further left I go, my graph is pointing up, which means my graph is pointing towards positive infinity. So these are your 4 cases. Even degree positive, they both face up. Even degree negative, they both face down. Odd degree positive, they're opposite and it ends up on the right side. degree negative, they're opposite, and it ends down on the right side. So what we're going to do now is we're going to take all of that information we just did and put it all together. So consider the following function. F of x equals 2x to the fourth plus x cubed minus x squared plus 5x plus 3. So a question would normally just say predict its end behavior. But I've broken it down right now into A, B, and C because these are the things you should be thinking of in order to determine the end behavior. So what's the degree? Degree, remember, is our highest exponent. So my highest exponent is 4. It's a fourth degree polynomial. So is the exponent even or odd? Is 4 even or odd? 4 is even. So I know that even is both facing up or both facing down. What is the sign of the leading coefficient? If I look at my leading coefficient, I have a 2. This 2 is a positive. So because it's positive, I know that even positive, they both face up. So as x approaches infinity, or as I'm going further and further right, where is my graph going? That arrow is pointed up, so it's going to infinity. As I'm going further and further left, it is also pointed up, so as I approach negative infinity, my graph also goes to infinity.